Okay. Hey guys. Namaste. All right. Today we're going to talk about section 11.1. All right. Make sure you're taking notes on what I'm saying, and let's go through it. Also, make sure you're doing the worksheet and book, and then you're also watching my other videos. Okay. So make sure you got that. All right. So in section 11.1, we're starting the science, which is the ultimate science in all of science, and that is the science of physics, which is a study of motion and energy and the universe in general. It is far superior than the sciences of chemistry and especially biology. All right. So, biology and chemistry, those are the slower, younger brothers of the science of physics, whatever. It's like we just kind of like let them tag along, whatever, but, physics is obviously the elite science and the ultimate science. All right. So, and, too bad you guys won't be able to study that until you guys are at least juniors, probably seniors, but, whatever. We all have our crosses to bear. All right. Okay. So it starts with frame of reference. Make sure you're watching the video. I do a whole video on frame of reference. And a frame of reference is something that is used to tell if you're moving or not. And these are good pictures because these are pictures from space. These are old spacecraft from like the Apollo program back in the 60s and 70s. But the reason why these are good pictures is to talk about frame of reference is because if you look at these pictures, you look at these spacecraft, and from these pictures, they look like they're not moving. When you're saying like, well, they're not moving, they're in a still picture. But regardless of that, the reality is, in order to leave Earth, you have to shoot something up at what's called the escape velocity, which is about 22,000 miles per hour. So in order for this particular Apollo spacecraft, which, by the way, is America. And in order for this to reach the moon, we have to get this thing going at 22,000 miles an hour. And so in this picture with the moon as the background, this thing is actually moving much, much, much faster than a bullet from a gun. All right. However, if you look at it from the frame of reference, where you're kind of moving along with the spacecraft, it really doesn't look like it's moving very fast. Okay, same thing here. These two, here's the lander. All right, that eventually people go in and they detach this and then land on the moon. But what would happen is the lander would normally be behind. This is called the command module when it's launched, and then after it's launched, the skin of the rest of the rocket breaks off, and this lander kind of floats out there, and this what is called the command module turns around and then links up with it, and then the two go on off to the moon. And relative to each other, remember, relatives means in relation to. In relation to each other, they're not moving all that fast. In relation to the Earth, where this is actually happening high above the Earth, these two things are traveling together in relation to the Earth, good 22,000, probably more than that, miles per hour. So are they moving fast or are they moving not fast? Well, in relation to each other, they're not moving that fast in that reference frame. In the reference, a larger reference frame where you encompass the Earth, they're actually moving quite fast. Okay, so that's the concept of frame of reference. All right. Make sure you get these notes down. You probably already got a lot of them down from the video on frame of reference that I already gave you. For human beings, the most common frame of reference is just the Earth that's around us. It's the four walls that's in your house. If you're in the car, it's the whole Earth environment that's outside the car that you see through the windows. Okay. And that's the most common frame of reference that human beings deal with. All right. Okay. So moving on. All right. Just another frame of reference, illustration. Here's a guy. He's standing inside like the crappiest vehicle of all time, which is a box with wheels. And he's like, this guy right here, he's like, I'm not moving. I'm standing still. And then this guy on the outside is saying, wait, hold still because you're moving. Well, in this guy's frame of reference, which is the vehicle around him, he's not moving. But in this guy's frame of reference, where he takes into account all the ground and everything around, this guy right here is moving relative to him. So just another illustration of that. Okay, this is going to seem unrelated, but you need to get this down because we want to get into the concept of something called a vector, which you'll get into in a moment. Okay, and we start off with these two concepts because the universe kind of works this way. There are two related concepts. One is called distance, and we need these when we study motion. You can't study motion without knowing the concept of distance. Distance is covering distance is motion. When you cover some distance in a certain amount of time, you're moving, okay? And how much distance you cover in how little time determines how fast you're moving. So what is distance? Distance is basically how far you travel. Displacement is how far you travel relative to a start point, okay? Displacement is basically distance with a direction attached to it. So here's a good example right here. I know the video thing is kind of covering it up a little bit, but distance, say, would be like 50 miles. If I say like, okay, 50 miles from myself, okay, great. Or if I say, hey, this object is 50 miles away from me. Well, that's great, but where is it? Well, what that really means is if you drew a circle around me with a radius of 50 miles, okay, the object I'm talking about could be anywhere on that circle, okay, 50 miles from me. But if I say 50 miles due east, that's a little bit more information. That now is a displacement that's a little more specific, just the fact that it says due east on it, all right, that's a specific point in space relative to a start point where I would be the start point. So if I say the object is 50 miles from me, that's a distance. If I say it's 50 miles due east of me, that's a displacement. I would be the start point. 50 miles due east would be the end point. And that's a displacement. Okay. All right. Here's just an illustration of this. Here's this line, squiggly line represents an object traveling some distance. So here the object starts and then it goes like this. And so this is basically would be like Mr. Kelly walking out of a bar on a Friday night, or maybe Mr. Leonard or something like that. And so the object would go in a random motion like that, stepping and backtracking and whatever, but kind of looping around. And the object goes its distance and then it winds up right there. So the distance would be however long this squiggly line is, like if you were to straighten it out. The displacement of the object would just be from here to there. That would be the object's displacement. Make sure you write that down. That's a good thing to get. All right, distance. So maybe even copy this, all right, in your notebook and write a squiggly line and say this is distance. And where the squiggly line ends, draw a straight line from the beginning to the end and say that's its displacement. Okay, here's another here's another illustration of this. Here's a house, and this dude is trying to get to work at this factory over here, and he's driving his bike, but there's some mountains in the way, so he goes like this, and he follows this kind of curvy path to get to where he works. And he goes a distance of 200, meters, whatever, miles, I don't know, a long way to drive to work, but let's say 200 meters. The displacement that he had actually only depends on where he started and where he ended up. It's a straight line path, okay? So his displacement would be like maybe 100 meters, okay? There is use for this. Just kind of bear with me as to why you need to know this information. Okay. Now, in old terms, there were old terms for things like this. Distance oftentimes used to be referred to in human past as, we would say, it's 200 meters as the wolf runs. Yeah, those of you guys who are into Dungeons and Dragons and The Hobbit and The Lord of the Rings, might know things like that. Why? Because a wolf is a ground animal and has to go around things. You would say the displacement is 120 meters as the crow flies. Why? Because a crow can just fly right over them and just take the displacement rather than the distance. All right, just kind of excess knowledge, but you never know. Stuff to make you sound smart. Okay, so there you go. Okay. This is a concept of a vector versus a scalar. All right. So this is one of my favorite movies, by the way. I love this Pixar movie. Anyway, and I love that guy too. But okay, moving on. All right. What a vector is, it's a quantity that has both a size and a direction. And size, there's a new word for size. We call it magnitude. Magnitude. Okay. So displacement is a vector. It has a size and it has a direction to it. A distance we would call a scalar quantity. A scalar is something that only has size to it. So, for example, a good example of a scalar quantity would be temperature. So, if someone were to ask you what's the temperature in the room, you'd say like 70 degrees. Okay. All right, it makes sense because you can adequately describe the temperature of the room with one number, just the size of the temperature. 100 degrees would be a higher or bigger temperature, and so on. It wouldn't make a lot of sense to say, well, it's 70 degrees Fahrenheit at due north. People would look at you like you're on some sort of hallucinogenic drug if you said something like that. It doesn't make any sense to say that for temperature. Temperature is a scalar quantity. Vectors are quantities that have both. They have a size and a direction. So, for example, airspeed velocity is a good example of a vector. In fact, sometimes you will hear the concept of the tower at TF Green vectoring an aircraft, because they will say to the to the pilot, make your airspeed 500 miles an hour, 30 degrees north of east. That makes sense. Okay, that makes sense. To not only have the size 500 miles an hour, that's the magnitude part, but also the direction, 30 degrees north of east. Okay, and a vector is represented by an arrow. Okay, so, and you'll see. Okay, you can add vectors together, and the way we add vectors together is by adding them the way we say it, tip to tail. Okay, so here's one displacement vector, 40 meters, that looks like about east, and then another one is 30 meters. All right, that looks like due north. The answer when you add these two things is called a resultant. Okay, it's a fancy word meaning answer, but again, learn the language, learn that word. The resultant is what you get when you add two vectors together in this manner. Okay. All right. If you're in a zombie apocalypse, rule number 18 for survival is to limber up. Okay. Make sure you get, your body, warmed up a bit. All right. Before you go into action. That's very helpful. Okay. So make sure you do that. Okay. All right. I know this was a short kind of slideshow here, but it goes with section 11.1 of the book. So go us out and enjoy your apocalypse.